Good afternoon, everyone, and welcome to the College of Engineering Virtual Brown Bag Series. Today we have a very exciting and timely presentation. But before we go to the presentation, introduce myself briefly. I'm Gautam Das. I'm the Associate Dean for Research, College of Engineering, and I've been hosting several of these Virtual Brown Bag Series events in the last couple of semesters. Today, the topic is going to be icebreakers, predicting and preventing ice buildup on roads and bridges. And the presenters are going to be two of our faculty members from civil engineering, experts in this topic, Nick Fang and Xinbao Wu, Professors Fang and Wu. And I'm going to introduce them briefly. But before that, let me tell at a high level what the talk is going to be about. Pavement icing conditions is a major concern for our transportation operations, especially during winter seasons. And this is especially relevant because all of you probably know about the massive car wreck that we had on I-35 on February 11th. And that was really due to lack of proper de-icing. And that's the reason why today's talk is going to be very timely. So while it remains a major concern for ground transportation, it's also a danger for air transportation operations. Icy runways can affect aircraft's ability to slow down, stop, and maintain directional control. So well-informed decision support systems and innovative technologies for de-icing and snow removal are really, really important. And today's talk is going to shed light on what UTA is doing in this space. And let me introduce the two speakers. They're going to respectively give their own expertise views on this topic. Professor Nick Fang, he's an associate professor in water resources at the University of Texas at Arlington. He obtained his PhD degree in 2008 in civil engineering from Rice University. He's the associate chair of the Academic Council for the Interagency Flood Risk Management Team, which consists of several different agencies such as the National Weather Service, the U.S. Geological Society, FEMA, and so on. He is a very celebrated researcher, actively performs research in the areas of urban hydrology, radar hydrology, large-scale hydrological modeling, disaster recovery, mitigation. He has a lot of funding from state and federal agencies. Our second speaker is Dr. Xinbao Wu, who is an associate professor at UTA, also in civil engineering. He got his PhD degree from Case Western Reserve University in 2009. And prior to UTA, he also worked as a research associate at the Louisiana Transport Research Center. And his research includes geothermal energy applications, deep foundations, bridge scour, and soil sensors. He has got some interesting projects with the Texas Department of Transportation, in particular bridge de-icing projects, geothermal bridge de-icing projects. He is a member of from the Transportation Research Board committees of various committees, AFP 220 and AFP 60, and so on. So both well-known experts in these topics, and it's my pleasure to invite them next to give the presentation. Before they start, just some rules of the way things are going to work. And they'll be speaking for maybe about 30, 35, 40 minutes. And if the audience has any questions, so there is a chat box. Please type in your questions there. And once the presentations are over, we will read out the questions to the presenters and they will answer them. Thank you very much.
Thank you. All right. So good afternoon, and thank you very much for this great opportunity for us to share this research progress. It's done by Dr. Yu and myself. And given the timely incident happened 2 weeks ago, the biggest, the daily pile up in Fort I-35. I think this is the kind of research update we want to really kind of give audience what we've been doing and something we can help local agencies and cities, to prevent such a disaster happen again. So let me just kind of go on to talk about a little bit why this topic is so important. Okay. So really, I mean, we are in the winter, and Dallas-Fort Worth in Texas, typically people think about Texas as a warm state, but we do actually experience a lot of winter disasters like these. So what you see here is typically Dallas-Fort Worth, for example, 2015 spring. We even have a 6-day closure. I mean, one fatality. I mean, happening right there. And on 2000 to 2010, we have a 642 events related to winter road disaster right there. And over years, I mean, they did a calculation. Annually, there's 7,000 people lives losses, I mean, over years, I mean, due to these winter road condition here as well. So one of the latest disaster we know, that's a 133 pile up. I mean, along I-35. I mean, that really is got a lot of national attention about these road condition. How are we going to prevent? I mean, us from this kind of disaster from happening in the future as well. So we are doing a lot of research at UTA and the Civil Engineering Department, and we'd like to share with you. Dr. Yu, you want to share a little bit about your opinion on this particular slide?
Yeah, thank you, Dr. Fang. I want to just highlight, you can see the photos. That I saved the photos about 5 years ago when I started the TechStart research project on geothermal bridge de-icing. What is showing also on that left photo, you can see there's a sand truck also as a vehicle just following the sand truck, which is going to treat the very snowy roads. On the right side one, the photo that's highlighted the I-35, the pile up, the crash, which is very horrifying to watch. You know, more than 100 vehicles involved. That accident. So what I want to point out here, what's important, of course, the cause of that accident is because of the icy roads. Well, there's a certain conventional practices should be done to do the pre-treatment. But the other things where the critical about the location is mostly happens on the bridges, which is more exposed to colder air. They are cooled much faster than the pavement. Dr. Fang, let's go back to you.
All right. Okay. Thank you very much. So really, during the winter, the cause of those really the tragedy is the ice being formed on the surface of the pavement, and people can easily drive on top of it without noticing the slippery feeling on that. So then you lose the control on the vehicle there as well. So that's not only for the ground transportation, but for air transportation there as well. So people thought, hey, airplane flying in the air, but they eventually got to land, right? So making landing and also taking off, they're going to take a lot off on the runway. So runway, there's no difference between the runway for airport to the highway condition there as well. So this is saying, I mean, we also kind of have another similar research. I mean, I have a 5-year contract with the Dallas-Fort Worth International Airport. One of the tasks they want us to do is provide a early warning system for their runway icing forecast feature for them as well. I want to talk about this slide here, why this is important as a road condition here as well, because the airport really is a business entity. Any interruption on the operation going to cost them money, and they really kind of pay attention to make their operations smooth and also reliable as well. So currently, I mean, the winter condition definitely going to make their operation interrupted, and so they need to have a decision to be made earlier so they can make a corresponding, plan as well. Secondly, here is based on this FAA's 2014 data, they know any delayed airplane they're going to cost about $82.66 per minute. So that is a huge amount of cost. If they see some unexpected winter condition coming in, there is a cost associated with that. So decision makers for business opportunity and business entity, they want to know what is incoming weather, how can they really minimize the cost or damage to them. So right decision is very important to them. And currently, unfortunately, I mean, a lot of airports, they do not have such a decision-making system out there. So I would say the decision-making system is a billion-dollar industry and market right there. And the researchers, we actually really looking to help them to to really kind of minimize the loss, and that is another way for them to make more profit there as well. So this is why we actually we've been working with Dallas-Fort Worth International Airport to develop such a system right there. And again, airport winter maintenance is a very critical issue in national security. That is, everyone understand this. On the right-hand side is showing 2019 O'Hare Airport. There's a airplane actually really kind of skid through, the wrong way. That was a scary moment, there as well. So everyone, working on in the airport, they know, maintaining the ground condition is very important. So for many people know, my background was really doing a lot of flood study, urban hydrology there as well. And one of the things that I do also for a living is develop an alert system there as well. So in general, this alert system, we take in a lot of reliable data and then going through the modeling and also machine learning data-driven analysis to come up with a right decision for users to make their initiate their strategy there as well. So this is the kind of system. We've been doing a lot of alert system for not only for the cities, but also for the state and the federal agencies there as well. For the large watershed like a Trinity River, we have a real-time data from different reservoirs and provide a decision-making strategy for those agencies to do a reservoir release and also running the model there as well. Our data could be kind of real-time, and then eventually go through a kind of a complicated modeling structure. We can come up with flood inundation and also, what are the flood mitigation strategies for those decision makers there as well. So that really means, that the decision-making framework is being done, and we can use a similar framework to apply to this icing forecasting feature as we're talking about here as well. So this is the kind of system we use for currently, for the DFW airport. And we use a state-of-the-art technology combining with a in situ, testing, which is done at a Dr. Yu's lab. There's I'm going to talk about details later. And all the technology combining with experimental information and will be integrated into a decision-making toolbox, and then that will process and generate a very reliable decision for airport to take either they're going to do de-icing and anti-freezing strategy for the airport during winter condition. So this is the kind of things that we right now currently working for DFW, and I want to make sure there's lots of data. Actually we evaluate it and also ingest into our system, like not only from a NOAA weather system, radar rainfall information. We also rely on the European climatic model weather forecasting system there, give us a short-term forecast. And we also rely on the FAA's integrated terminal weather system. And with the DFW, it's their own weather system there as well. So not only based on those information which you can access, but we rely on those in situ thermodynamic forecasting observation data they have there as well. So it's a very reliable system, data source we actually retrieve, and then we can serve the information to the airport to enable them actually to make a proper decision right here as well. So here's what I want to show, a very kind of complex system, the data stream we actually receive. 6 major data sources we currently actually take in. And on the top left is a National Weather Service radar. Give us an overview. See what is the weather coming into the DFW area. And also FAA have their terminal weather system, which can give us a more detailed information to each individual terminal. And then the European model, which is currently, people is talking about, is a more reliable. So for weather forecasting, so will give us a kind of a regional scale and a continental scale. So weather forecasting data there as well. So Weather Service also provides their temperature forecasting, but that's at a larger scale, and we need to combine that with our in situ data, which is down below in the middle. Then combine with all the individual sensors they install, and then we can combine them together to give us a forecasting on the temperature. So I know a lot of people in the audience that you talk about, hey, this is all the data you use. How are you going to really make sure those data is really tailored and suitable for airport, DFW airport alone? So we need to actually go through another in situ testing here as well. So for this particular project, Dr. Yu's expertise is he can really have a big enough ice box and to simulate the temperature variation in reality. And we actually took on the right upper corner, you see that is a illustration of a concrete block we actually got cut from DFW airport, which that represents runway concrete. That is about a 21-inch thick, and we have about 24 inches wide and 36-inch long. And we actually carry that block, actually bring into UTA and into this ice freezing box right here. And for all the icing scenarios, we generally actually divide it into 3 different conditions. One is for the gradually cooling temperature drop down, see how ice being formed on the surface on this ice concrete. Also, we have a rapid cooling. Sometimes we have those rapid temperature drop in airport, and we want to see how the ice being formed under this rapid condition. But the third thing is a very challenging one called the black ice condition. Really, that means when the temperature dew point changes, that means and also that got to shows the ice, very thin layer ice gonna be formed on the top of a concrete. That is one thing is very, it's dangerous there. It's called black ice condition. So in this ice box, we have a mixture to mimic, the rainfall in there. And so this is a kind of very in situ, condition, and using all the simulators, and we actually derive a lot of relationship between the temperature and icing timing there as well. So on the lower picture, basically showing when surface temperature drop down lower than the dew point temperature, that is where ice gonna be formed, and we use that guideline. Actually, it's really kind of direct our experiments down at the UTA. Dr. Yu, do you have any comments on this particular slide?
Well, I just want to highlight that in the laboratory environment, we successfully recreated that black ice phenomena, which is very exciting. We tried a couple of times. Finally, we got a really good black ice in the laboratory environment.
Yeah.
Thank you.
You're welcome. So this is the kind of experiment will be the support evidence for us to derive the relationship, and we can use into our decision-making system here, which I'm going to show, as example. So during this, right before, Valentine's Day, February the 14th, we know there's a cold weather coming in, and we alert airport and we say, hey, so the temperature going to drop, and there's a rainfall event coming in, because when rain coming in during the dropping temperature, that is not a good combination, and they really need to look forward for some preparation for there as well. So I want to show you, during that event, we start watching, the system start watching the information from their local sensors. Those are the sensor locations that show on this particular spot. For airport, you have A, B, C, D, E, there as well. So you can see that DFW airport, they have all the sensors, for different terminals. And the weather system is coming in. You can see that is moving pretty fast, and there's a timing. So this is the weather system. We have a data, actually pattern recognition. We can really determine what is the moving pace and how fast this weather system gonna arrive for the DFW airport runway. So you can calculate for the timing. The lead time is very important. And then, so there's a model system, as I mentioned early on. They provide hey, order in the blue area, they're gonna have a freezing, condition right there. But as you can see, the warning be given a large area is DFW in the red boundary, and this is a pretty large scale. Very coarse resolution, and we want to actually airport wants to have their own tailored decision for them for airport, because when you make a decision yes or no, and that is as same as important as when it's going to happen. So this is what's the really complication of a decision support system here as well. So our system is able to to tell when it's going to happen, or first if it's going to happen, and when it's going to happen there as well. So I will show you the next one right here is a archived data with our model simulation showing, hey, this is when the time elapsed. When is the temperature going to really drop? What you see here on 4 different lines right here are very important. One is the runway surface temperature air temperature and the runway dew point and also the relative humidity. When you see the relative humidity rising, that is surely is an indication of rainfall is coming in right here. And the surface temperature is very indicative for us to know when the surface temperature of the concrete gonna drop down below 32. So if you see the surface temperature drop down, then 32, which is represented by the black line, 32 is the freezing point. And you know, I mean, and given there's a rain coming, you know this is kind of going to be ice going to be formed on the runway. So during these dynamic, performance, so you can see if, the icing going to really be formed and when it's going to be formed there as well. So let me show you a overall prediction. So right now I took out the two different kind of data source right here. One is the yellow line represents a dew point temperature, and the blue line red line showing this is surface temperature. You can see the surface temperature keep dropping. The dotted, the surface temperature is from our forecast. You can see the forecasting is pretty much in general direction with the real data. So it shows that some fluctuation right there, but eventually it shows very good. Match right there. So I want to show here exactly that's the moment ice being formed, and we actually gave them 2-hour lead time, which means that's what exactly airport wants. Because 2 hours lead time they need to mobilize their engineers, technicians to really kind of do their proper anti-freezing strategy right there. So, but for this particular storm, and we actually gave them a warning ahead, and they really kind of know it's really coming there as well. So these are the first event we tested using our system, but in the future there's more events we're going to come in. We're going to test it and show more archive a lot of events we can share with you as well. Okay, so this is what I do. I do the decision making. But when we get into the point, say, hey, once we receive the decision, how are we going to do it? So Dr. Yu, you got to talk about, hey, how are we going to really kind of prevent or just kind of warm up or melt this ice on the road, on the bridges? And he going to show some innovative technology he developed at UTA, and he going to share with us.
Dr. Fang's presentation highlighted the importance to get the information, make the ice forecasting. As general public, we sure want to stay informed. We watch our weather forecasting. We plan our travel. The best way, if you just plan, if you can avoid to be hitting on the road on the icy conditions, I think that's the best way to do it. But for the transportation agencies or the airport, they want to know that forecasting information. They make proper plans. They can either do anti-icing or pre the storm event, or do the de-icing and snow removal during the storm event. So here I'm going to talk about a particular new technology using shallow geothermal energy to de-ice bridges. So currently, if there's ice on the roads and the bridges, the current practice is to apply de-icing salt chemicals and also apply the sand, which is we see that in the last week we see some of the trucks being on the road. They do very busy to do the treatment. So, but for those traditional methods, de-icing chemicals, there's problem. They associated with the side effects like the corrosion to the bridges and the roads and cause damages, and of course also the cost. The other things for the sand, there's a problem, skid. Right now, when I drove on the road, I still see a lot of debris left because of the sand treatment. So the challenges with the existing methods is the cost, fuel consumption, traffic delays, lack of equipment, and manpower. Particularly for southern states like Texas, we are not really have those stock that equipment and those de-icing chemicals, particularly in large demand for this record storm event like this. For de-icing chemicals, that's the typical snow plows to during the storm that is more effectively to remove the snow on the surface. During the storm last week, I do see there's a lot of snow plows. Probably is we borrowed from different states and they come here to do the cleaning. Using de-icing chemicals, here we did a study in 2009 that to look at what's the cost. You see here we have different de-icing chemicals and their cost. Each state DOT depends on the location, the size. They spend at least $1 million each winter to do the winter maintenance and the de-icing operations. So here highlights some of the challenges and then the problem associated with the current using the de-icing chemicals. The corrosion is a big problem. On the left side, the bottom of the photos shows bottom of the bridge deck, which you see the concrete already spalling off. The concrete rebars is highly corroded, and they need at a certain time they need to major repair. I talked to some of the DOT engineers in the northern state. Some of the new bridges, they have to go through a major repair even just up after 5-6 years of operation. So that's a big cost to do the repair. Another is related to the environmental contamination with the de-icing chemicals. They goes with the rainfall, the storm water. They run into the groundwater system. They can do harms to the wild animals, to the plants. So more problematic is the potholes. During each winter event, we see the road condition got to deteriorate really bad. More exaggeration, you can see some pothole size that can become a little swimming pool. Alternative to using de-icing salt is this technology is called a heated pavement or heated bridges. So this technology is nothing like new. You see showing on this photo in the 1980s. That's the heated pavement technology is being implemented in Louisville, Kentucky. Here they show some of the photos after the snow melting in that event. The highlighting in the photo on the left is the pavement, on the right side is the heated bridge deck. So both the pavement and the deck can be heated using this technology. But traditionally, the heating source can be coming from different energy sources. They can do electrical, do the snow melting system, where they inputting some embedded heating cables in the concrete pavement, or they can make the pavement itself to be conductive. As far as using the heating energy source, they can using traditional fossil fuel to do a boiler type of the heating as well. So that comes to the second type, heated pavement using this hydronic type. Hydronic type, in contrast to the heated pavement using electricity, which is using mostly cables, embedded wires. The hydronic pavement, the second category, they're using embedded loops, which is embedded into the pavement in the concrete. During the loop, they are circulating the heating fluid. That heating fluid can be heated up by the fossil fuel boiler or the electricity run boilers. So in this new technology, we are using this new source called hydronic heating system with shallow geothermal energy. So here shows our design, where you can see a bridge deck on the top. Those red dots represent the basically they are PEX pipe filled with a heating fluid. That heating fluid I'm gonna explain a little bit later, which is circulating through a closed loop. The other part of the loop is embedded in the underground. After circulating in the underground, they bring up the warm fluid and to the bridge deck. For the design of a hydronically heated bridge or pavement, it's very important to consider those different environmental factors. We all know that the bridges, the icing is affected by environmental like ambient temperature, wind speed, and solar radiation. A lot of those factors has to be considered in order to do a proper design of the heated pavement. So we have to consider all this. In terms of the bridge geothermal de-icing system or operation, this diagram illustrates the entire system, how it is being operated. You can see in the diagram, there's where the bridges needed to be for de-icing operations. Those loops represent these PEX pipe loops. They are run underneath or inside the bridge deck. This system is being connected to a heat pump through a flow center. And the other side, under the ground part, is the ground loop heat exchanger, which is basically banded pipe loops inserted into the ground. In the loop system, you have the heating fluid, which is driven by the flow center. They just keep running. During the de-icing operations, the cold fluid that comes from the outside the bridge deck and then goes into the ground. After it goes through the entire depth, they bring the heat from underground and bring that heat eventually goes to the bridge deck and heat the bridge where it's needed. You can also see on this diagram, we have a very important component, which is weather forecasting, icing forecasting. With that information, they can using automatic control system. We can control this de-icing operation. Like a pre-storm, we know the storm is gonna come in, then we can have the system turn on. We call it preheating, which make the de-icing and the snow melting much more efficient. If we don't have that information, we wait until the storm's ice to starting to formulate on the surface and turn on the system. That will be there's a delay effect. So will be more energy consumption. So what is geothermal energy? So we heard about geothermal energy a lot of the time, but typically when you refer to geothermal energy, they refer to very deep hot geothermal energy, which can be directly using for electricity generation. But for our application, we are more focusing on this term called shallow geothermal energy or low temperature geothermal energy, which is we only don't need to go that deep. We're going to go to as far as like 100 feet below the ground surface. Here shows the map where the seasonal ground temperature distribution all over the United States. Just pick that point. We give you the temperature profile. It shows here. Here shows the temperature variation, winter, fall, and summer. You can see at a certain below certain depths, that temperature maintains almost constant year round. So the geothermal energy will utilize this constant temperature during the winter time. The ground becomes hot compared to the ambient, and during the summertime, the ground becomes cooler than the ambient. So we utilize the temperature difference and can do heating or cooling. One of the components using this de-icing system is the geothermal heat pump. Geothermal heat pump to a lot of people is not unfamiliar with some newer home or smart homes, energy efficient home equipped with the geothermal heat pump. So here just illustrating using a geothermal heat pump to do heating applications. You can see here you can use it to a heated floor if you that make your home more comfortable. So what it does, you see there's two parts of the system. One part is under the ground. The other part is where the application side. These can be applied to the floors or the bridges. When the system is running, the fluid is running through this loop system. Again, as I mentioned earlier, during winter time, your outside air temperature is freezing, but the ground is still relatively warm. So with that fluid circulating through the ground, it brings to the warm fluid. And the heat pump, what it does is very energy efficient. Typically, heat pump have energy efficient cost to the input energy ratios of like 5 to 4. So which is very energy efficient. So that can input using the electricity to input additional heat if we want to bring to the very comfortable level of heating to the house. So that's for the heating operation. During summer, where we want to do the opposite, instead of bring heat into the house, we want to remove the extra heat to the outside. But the conventional, the HVAC system, where you just work with outside air, when during the summer operations, outside air in Texas in particular, we have a temperature more than 100 Fahrenheit, where you want to dump the heat into the very hot air. That's very difficult. You have to using a lot of electricity in energy in order to overcome that thermal ingredient over there. If you're using the geothermal system, underground temperature is relatively low, 60 Fahrenheit during the summer. So we can easily to more energy efficiently to remove the extra heat into the ground. So this is the operational principle for geothermal heat pump. But when we utilize in the harness of the shallow geothermal energy, so we utilize this underground heat exchanger. So basically what it does is just either dump heat into the ground or extract the heat from the ground. It depends on the seasonal application. The system can do both vertically. That's what we currently do in our geothermal de-icing project, or you can do this horizontally. So the difference is horizontally, for those people, you have a really large backyard, you can do the horizontal loop. For those you have a smaller yard, you can, because the space is a concern, you can go deeper, then you can do a vertical system. In recent years, we combine these loops with a foundation system, which I'm doing geotechnical engineering, do a lot of foundation. We build new buildings or bridges. Typically, we're gonna do like a concrete drill shaft. We're gonna drill to the soil anyway. So during the construction of the drilled shaft or the energy pile system, so what do? We just lower those heat exchanger, those plastic pipe into the concrete rebars, then combine with the concrete casting process. So we mix both as energy pile also can support the buildings or bridges we are using. So there's really a innovative designs for that happens in last decades. So here shows the system we are doing at the UTA, this TxDOT funded research project. Here shows the schematic design for a geothermal mock-up bridge. So what are we doing here? We have the underground, the heat exchanger, and we have a control room. We have the flow pump, the heat pump connect to the loop system. And on the other side, where we build a mock-up bridge, we're building two types of heating system because traditionally a lot of people they doing this hydronic or geothermal heating. The pipes is embedded in the bridge deck. And on the other side, we are doing here is called external heating. We are more targeting the existing bridges where the heating pipe system can be attached. You can see here attached to the bottom of the bridge deck, which is more targeting a large amount of bridges which are already being built. We can implement this heating system by retrofitting the bridges, which is more easier and more in large demand. So the next slide shows the our construction of the geothermal bridge. This happens about 3 years ago. Here shows the timeline we did with the construction. This is the mock-up bridge we are building. TxDOT give us some help to lifting the heavier members to do the placement, but as far as all the details, the tie the rebars, tie this the heating loops, all done by our students here at UTA. Here shows the drone footage where the concrete casting on the top. This is during a relatively hot day that we have to cast the great amount of the concrete in about 2-3 hours. That was really challenging during the construction time. I want to highlight the difference of these loops. You see the red PEX pipe. I think the past weeks probably you know more about PEX pipe than any other time. You know, PEX pipe is really good materials compared to the traditional copper pipe. You know, they are more easy to be pipe bursting during this kind of freezing weather. These are more newer, nice materials. So I utilize this embedded in the concrete rebar cages and casting in the side of the concrete. The other one I talk about, this is the external heating, which can be implemented on existing bridge. Here we apply some cement mortars between the PEX pipe, the concrete deck to increase the thermal contact to make the heat transfer more efficient. Then after we place the this PEX pipe, we cover it with a polyurethane, these insulation materials to preventing the heat loss to the bottom, to the environment. We want the heat more go directly to the top. Well, these are more photos showing the more critical components, which is where we get the heat from, which is the ground heat exchanger. You can see the heat exchanger is just, you can imagine this is a vertical pipe, then you bend it in the middle, and we drill a hole using this drilling machine to a ground about 400 feet deep. Then you insert that bended this plastic pipe, this HDPE pipe into the hole. Inserting that could quite a challenge, is relatively long, 430 feet, because you need several manpower to insert it. So this is the look after everything is being inserted into the ground. This is before the cleaning up. We have the cables for the temperature monitoring. Another photo shows the different monitoring system. where this shows the horizontal loops, where from the vertical locations, we have to bring this loop system into our control room. Just ironically, this happens during the summertime, the record temperature, more than 100 Fahrenheit. So when we do the project for geothermal de-icing. Here shows what it looks like inside our control room, which is the brain, the heart, control how the system to be run. Here is the geothermal heat pump. What is very interesting about geothermal heat pump, when the system is on, even when you're standing right next to it, you almost hear nothing. So which is a great benefit if you can't, with regular HVAC system, you always hear the noise when the fan is on. So this is great. So here there's a flow pump, flow center, which is power the fluid flow through this system. We attach the thermocouples to measure the temperature, different location on the loop. Here the flow meter shows how much flow rate we get. Different instruments to show the temperature monitoring. Well, here now comes the fun part. After first being built 2019, we started to do the de-icing test. In a couple of several winters, we are waiting. We are waiting for a real snow event to test the system. But 2019, that winter, there was not much of a snow or winter precipitation. What we did when the temperature is below freezing, we are using a system. We're testing the system. You can see here we're using the thermal imager to take the temperature measurement of the surface. You can see the heated zone, which have a temperature 32.6 Fahrenheit. We also validated with handheld the thermometer to measure the temperature. This with not heated zone, so it goes contrast, which is 20.4 Fahrenheit, is much below freezing. So here comes the most fun experiment we done with the students. The device here we are using is the snow gun. We look at the outside ambient temperature. When we determine the temperature environment is ideal, we perform the de-icing test. So what is created? You created a lot of ice palette. You can see a close look of the ice on the bridge surface, the deck surface. And those here shows the result where without heating, probably cannot see very well, is covered with a very thin ice. But with this highlighted area is the heated zone. This is maintained above freezing. There's no ice accumulation at all. So here another close look. You can see between the transition, the heated area, unheated area. This is the clear covered thin layer of ice. Here it maintains ice-free condition. And more results for the second de-icing test. Here that we're using using the infrared thermal image to measure the heated surface. We get a good temperature, 33.5, well above freezing. And non-heated area for this winter event, we get 18.5 Fahrenheit. Again, the validation with the handheld the thermometer measurement. Well, summary and findings. Apparently, the ice forecasting system is very important. We need to get us informed for our transportation agencies. We can make a proper winter plan or pre-treatment during or after the snowstorm. And for the geothermal heating system, I want to emphasize that we are using a renewable energy system. We can increase the driving safety and extend the bridge life. We also did a cost-benefit analysis. If you consider the bridge design life with 50 years, one investment we can get 10 times the benefits back. We did design and construct this mock-up geothermal heated bridge. The underground loops is 430 feet. We heated area is 192 square feet. The geothermal heat pump is 3.5 ton. And this geothermal de-icing system can maintain ice-free condition at this 25. The lowest temperature during 2 de-icing tests. That's what we tested before. The last slide, I want to show you guys what we saw the newest result in the last week, where right after the major snowstorm, I managed to drive to the site, took this photo, which shows really a good snow melting performance of the UTA geothermal bridge. Well, with that, I conclude the presentation. I will take any questions you may have.
Gautam, you're muted.
Oh, so thank you. Thank you, Nick and Xinbao, for a great and fascinating presentation on some of the research that you're doing. So at this point, I would like to invite the audience to type in their questions, whatever questions they may have for the presenters, and I will read them out. So while that is happening, I actually have a few questions of my own. So one of the things I didn't hear today is the cost of some of these de-icing systems, or maybe this geothermal renewable energy exchange systems. Do you have any insights to share there? How do they compare with more conventional methods?
Yes, Dr. Das, this is a great question. So starting with this research project under the higher textile DOT, the administrative, they are really concerned about the cost. As far as any practical technology implementation, the cost is very important. Just as our regular homeowners, if you want to invest, a lot of people are trying to sell you either the solar panels or you can install the geothermal HVAC system. The cost is the first thing you want to think about. So I don't want to give you a detailed number, which is based on the size of the bridge, the other detailed design. But I think a more fair evaluation to look at the cost versus the benefits. We published a research study, a paper about 3 years ago. So what are we looking at? We look at the construction cost, the material cost, the labor cost, also the maintenance cost to implement this system on a bridge. We selected a candidate bridge, a practical bridge, and we implemented the system. The cost data we utilize is from the previous published data. So we did this cost analysis, and then the benefit, we look at the benefit. Our number one benefit is the safety. Particular in the opening of this presentation, you see the horrifying, the I-35 wreck system. This itself took away like 6 people, and more than 30, 40 people, more than that, is injured that went to the hospital. So the safety is really the biggest benefit of this. So we're taking that is hard to measure. Okay. Another thing is, we are analyzing the benefits is the traffic detour. If there's an accident, a lot of people are going to be delayed. That's everybody's fuel cost, additional fuel cost, or the manpower loss. We all take that into consideration, and also the benefits, including providing much environmental friendly bridge system with less maintenance requirements. We take it into all consideration for a typical bridge with 50 years of design life. So if you invest, let's say if you invest one investment, the return is 10 times the investment in over a 50-year period. Hopefully that answers your question.
It does to some extent, but I think it also will depend on how frequent do you expect this de-icing operations to be required? Like, for example, in Texas, yes, it happened, but it's not as frequent as, let's say, Minnesota. So maybe in Minnesota, putting a system which has a lot of upfront cost, but after that running it is fairly cheap is a better idea than maybe a place like Texas, where maybe more conventional methods can be used for the rare times that they are needed. So I'm just speculating.
Yeah, I totally agree with you. We have to pick a typical average scenario when we do the analysis. Mm-hmm. Definitely is geographical related. Also the traffic amount, all the other factors is related. So I just compared the traditional system. So the traditional system, of course, just one single event operation is much cheaper. Is everybody doing this? They already have a way of doing that. So of course, the initial investment is big. Just like when you put on geothermal, the solar panels, you are gonna put down a lot of initial investment. So that's what I'm gonna say. But if you want to do annual cost analysis, then this one is gonna be very effective.
Yeah, and also I want to chime in, add one more comment right here is there is a cost about the public perception. So for example, what we had last week, I mean, the snowstorm, and make Texas very well known among other, I mean, states, because I mean, they would probably say, hey, Texas barely see this kind of snowstorm, but once we have it, the whole system just went down. I mean, so this is the thing, as there's a cost of that too. So even though Dallas, Fort Worth, Texas rarely kind of experience those compare with Minnesota, but once that system happened once, I mean, and that actually will turn the public perception really upside down right here. So there's another thing to really, for a lot of agencies, they are thinking about it as well.
Okay.
Yeah.
All right. Thank you very much. Now, there is a question from the audience, so I'm going to read it out verbatim. So, icing forecast systems highly depends on the forecast products like ECMWF or NCEP data. The problem so far, the forecast product still has an uncertainty, which differs in each forecast data. How did you address this problem in your icing system?
Yeah, this is a very, very good point. I think it must be from somebody who has a very good knowledge about weather forecasting. I mean, maybe it's from my colleagues here. So really, yes, there's uncertainty from the weather forecasting. The good thing about our system here is we have in situ sensors right there. And in situ sensors give us more reliable, I mean, data at this moment. But really the forecasting feature here for us is that we want to use the ambient temperature that transfer to this the concrete. I mean, because as you see early on, just because you have a ambient temperature lower than 32 doesn't really mean your concrete, your pavement temperature is going to drop to 32 as well. So there's a delay right there. So that's what we actually combine, actually using the laboratory tests, I mean, at UTA to really see those temperature change, given a different ambient temperature, see how fast the surface temperature on the concrete drop down as well. So we have a very comprehensive coverage on the different scenarios to test on these. So this is a kind of, we thought ahead. I mean, we believe there's an uncertainty in the weather forecasting. So that's why we use in situ data. And plus, I mean, our laboratory test to really to make up this, this gap right there.
Thank you. I'm going to read another question from the audience. If the geothermal heating system was used in a large scale, is there any environmental effects, for example, destroying the temperature profile, which will affect the soil?
Yes, that's really a good question. So design a well-balanced geothermal system is very important. You know, for example, it depends on the climate condition. Where is the cooling demand more dominated, or is the heating demand more dominated? So for long-term operation of the geothermal system, we have to balance the temperature profile. So we can do two kinds of operations for our particular geothermal bridge during summer, where apparently no heating is needed, but it's opposite. The bridge surface is gonna get so hot, so we still turn on the system. So the hot fluid, the heat, gonna be circulating into the ground. So we call this a thermal energy storage or thermal recharging during summertime. So then we design the system in a way that extra heat we collected can be used during the winter de-icing operation. So we balance. So the goal is to achieve almost minimum temperature disturbance to the natural ground. So we can be very sustainable even for a large scale system.
Okay. Thank you very much. So we have another question from the audience, and this is no other than our Dean, Peter Crouch. To cut costs, we still need weather prediction and the variation across relatively short distances. How to incorporate this?
Gordon, can you repeat the question?
Yeah. To cut costs, we still need weather prediction and the variation across relatively short distances. How to incorporate this? That's the question.
Okay. So I can see, I mean, the weather forecasting is also going to play play a very important role in this decision making. I mean, obviously there's uncertainty in the weather forecasting information right there. But for short distance, how that really kind of come into this distance, I think that needs a combination of the weather and also in situ sensors. I mean, being combined together. That will give us a very good, actually reliable, forecasting information right there. And so I would say, this is a kind of decision is very important for any agency. For example, for the airport, they rely on decision to take a proper, strategy. But meanwhile, they also consider about, hey, if they make a decision only rely on one source, they rely on that, they're probably going to overdo. What does overdo mean? So if they apply de-icing fluid, which is a glycol-based chemical, they apply too much, that kind of make an impact to the environment. So this is the kind of decision they want. We just want to have a precise decision so we can cut down the consumption of this de-icing fluid, which got to really help the environment right there as well. So there's a kind of couple things. The weather is important, but in situ data combining, they're going to enhance the precision on the decision process there.
Okay, thank you. One more question from the audience. I'm going to read it out verbatim. Several years ago, I visited Iceland and learned that they were using geothermal energy to keep their parking lots and sidewalks ice-free. Is that technology similar to the one you're testing here? Does the difference between their typical weather conditions and ours requires a difference in approach?
Yeah, yes. Thanks for the great questions. Yes, in the Europe or the North Scandinavia countries, the geothermal is very popular. Particularly Ireland, they have maybe a very similar to our area like Yellowstone. Colorado, some area you have very close to hot springs, which make utilize the geothermal is much more convenient. So the idea is very similar. The whole technology operation is very similar. But as far as a specific geographic location, the natural resources available, we can make a lot of different adaptations to better utilize the geothermal energy.
Mm-hmm. Yeah. And I want to add one more comment right here. So that kind of inspired me a little bit here is during the last week winter storm, I saw a lot of people worry about their swimming pool, being kind of really caused by the icing being formed. I would say this is a geothermal based application really can be very useful to prevent the swimming pool, the water in the swimming pool be kind of forming ice. That is another kind of thought. Right here. Okay.
Thank you very much, Dr. Fang. Actually, I just want to add into that a little bit story. I did get a call last summer. There's one of the people I'm collaborating with think about building a swimming pool on his own backyard. He did think about to put a geothermal system around the perimeter in the walls, to keep the pool warm during the winter time. So thank you very much.
Yeah.
All right, moving on. We're getting close to the end of the hour, but we have lots of questions coming in. So weather forecasting is also very important for photovoltaic energy sources on the grid in the summer. So weather forecasting over short distances in DFW seems to be something we should consider for multiple purposes. So I suppose everybody would agree with this.
I would say so. Yeah,
absolutely.
Okay. So I have a question. Geothermal heating and cooling for transportation structures like bridges is a little bit different from for residential structures like homes, right? First of all, the scale is different, and secondly, yes, the temperature differentials are a lot different, right? In a home, you want it to be cooled to 68 degrees in the summertime when the outside temperature is 100 plus, and vice versa in wintertime. Whereas for a bridge, you just need to drop it to above freezing in the winter, right? So does that say that geothermal solutions for the latter is a lot easier than for things like homes?
In my opinion, for homes, mostly they combine it with geothermal heat pump, which is really, geothermal heat pump, even without the underground loop system can work itself. So a lot of redundancy, and also to be bring the comfortable level to the home living level is much more stringent as compared to this outside the infrastructure application. But the infrastructure application major demand is the harsh environment. We have to make the system work during the most harsh environment. You have to make it work. So the size scale effect is the most difference. Yeah.
Well, thank you very much. I think we have had a great conversation today, and I'm sure there will be a lot of other questions, but we have reached the end of the hour. So if people in the audience have further questions or would like to learn more about the research of our faculty members, please feel free to reach out to the presenters. And with this, I will draw this presentation to a close. Thank you, everybody, and we will see you at the next brown bag.
Thank you.
Thank you all. Bye.
Bye.
Okay, we're done.
All right. Thanks, folks. I think it went very well. Yeah.
Yep, very good. All right, talk to you later.
Bye-bye.
Bye.